Free falls and projectiles. Free falls, that is a special case of one-dimensional kinematics where we know what the acceleration is. Acceleration is implicitly gravity. Gravity, the number that you use for gravity, depends on what unit system you're in. So gravity could be 9.8 meters per second squared, or it could be 980 centimeters per second squared, or it could be 32 feet per second squared. Now, we typically write gravity as negative because it is down. So you will usually see it written with a minus 9.8 or a minus 980 or a minus 32. Now this is a case where the object is flying through the air but it's not under the influence of anything but gravity. So only gravity is acting on it. We do not consider air resistance. We don't consider any wings. So no airplane wings, no birds, no bees. And we also don't consider any engines at all. So we're not talking about rockets here. Or if we do mention a rocket, it's after the rocket engine is spent and it's coasting. So just things that are effectively rocks. Not even ping pong balls, because air resistance on ping pong balls is noticeable, but on rocks air resistance is not noticeable. So anything that we talk about basically boils down to a rock. Let's take a look at a couple of free fall problems. And the first one, let's have a person throw a ball straight up at an original speed of 25 meters per second. Now, we care about this only after the ball has left the person's hand and it is flying through the air, goes up, comes back down, and we can ask a couple of questions about this. Question number one would be, how high does it go? And question number two is, how long until it hits the ground? For both of these guys, we need to make our Woffinstat chart. And for how high, so for A, how high, we'll have the ball starting at 25 meters per second. The definition of how high involves it stopping at the top there. So that means it's not moving for just an instant. We're looking for the height at which that occurs. And because we are in meters per second, that means gravity is going to be at 9.8 meters per second squared. And what we need to do here is figure out our negative signs and our plus signs. We have the ball traveling up, and we typically call up positive, so we'll call this number positive. Gravity, however, always pulls down, so we'll throw a minus sign in front of that 9.8 to indicate that gravity is going to pull down. And it doesn't matter where on the path it is, gravity is going to be pulling down. Gravity pulls down the entire time, leading to the saying, whatever goes up must come down again. So gravity pulls down the entire time, so we'll put a minus sign in front of this. And since we don't care about flight time for the first half of this question, we could ignore time, which means that we will be interested in using our no t equation. And when we plug numbers into that, we will square the 25. Don't forget the 9.8 in when you put it into the equation. Using our calculator and the rules of algebra, we can have 0 equals 625 minus 19.6s. Now we need to get the s by itself, which will require a couple of steps of algebra. First, we're going to add the 19.6s to both sides, and then we're going to divide by 19.6 to get it away from the s. So that gets us the maximum height that this ball will travel to is about 32 meters, which is pretty high. But then again, 25 meters per second is about 55 miles an hour. So that was a pretty hard throw. For part B, how long was that flight from top to bottom? We're now asking about a different part on the flight path. So we will need a new kinematic variable list. We will still use 9.8 meters per second squared because gravity is not going to change over any of that flight. It started at 25 meters per second, and now we care about when it reaches back the same level from which it was launched. So now s is going to be 0. And this time the question is, how long did that take? So since this time we don't care about the final velocity, we can use the no VF equation, and we can plug in the numbers that we have. Doing a little bit of arithmetic here and factoring a t out from both terms, we get a quadratic here that we can solve without using the quadratic formula. Since we factored this, we can solve this by factoring. First we set t, this factor, equal to 0, and then we set the other factor equal to 0. So 0 equals t. Well, that was the time of the launch. That's not interesting, and that's not what we're interested in. What we're interested in is when the ball hits the ground again. So 4.9t equals 25. Divide both sides by 4.9, just like we did in part A. And we end up with 5.1 seconds. So that ball went to a height of almost 32 meters, and it took a little over 5 seconds to come back to ground level. Legolas shoot an arrow directly down onto an orc. And let's have him shoot that arrow initially at 250 feet per second. And let's say that at Helm's Deep, the walls are 400 feet high from where he's standing to the top of that orc's helmet. Keep in mind this time, instead of throwing the ball up like we did last time or shooting the arrow up, Legolas is shooting the arrow straight down. This means that we're going to need a negative sign in front of that original speed. Also keep in mind that the arrow is going to be traveling from the top of the battlement down to the ground level, so this 400 is also going to need a negative sign in front of it to indicate that the arrow is traveling down. Let's make our kinematic variable list. Now, since we are in feet per second and we put the original speed of 250 feet per second here and the distance that that arrow is going to travel under displacement, we're going to need 32 feet per second squared as our preferred gravity. There are a couple of questions that we can ask about this. Notice it's the two kinematic variables that we don't know. And the first one is, how fast will the arrow be moving when it reaches the orc's helmet? Well, since I'm asking about the speed here and ignoring the t for the moment, we can start with the no t equation. And don't forget that when you square a negative, it's going to become positive. And as we plug in these numbers, and there's no algebra to do here, it's just arithmetic. The last step that we're going to do, because we need to unsquare that VF, is take the square root, and remember that the square root is always plus or minus the number. In this case, that arrow is going to be traveling down. In order to indicate traveling down, we need to choose the negative of our two options. So it will be traveling down at negative 296 feet per second. For part B, we can ask, how long did that take from when Legolas released the arrow to when it hit the orc's helmet? Now we can use the final velocity, negative 296 feet per second, to calculate the time. This will help us avoid using a quadratic. So 296, remember it started out going down at 250. And we have a two-step algebraic equation here where we will need to add 250 to both sides. And then we will need to divide both sides by negative 32. Now it's very important that you don't lose any of your negative signs here, because you might end up with a negative time if you do that. And this means that it took approximately 1.5 seconds between Legolas releasing the arrow and the orc getting hit. Now that's enough time to dodge, so clearly the orc is not paying attention if he gets hit in the head.